All right, hello everybody, and welcome to another installment of Chapter 0 of the U.S. Navy and U.S. Coast Guard Damage Control Assistant Senior Enlisted Curriculum. I am Lieutenant Timothy Mueller, and I'll be the instructor on this lesson on fluid densities and the calculation of volume. All right, so the first thing we have to do is take a look at a couple key topics and a couple key terms that are going to follow us through this lesson, the next lesson, and subsequent chapters. So the first thing we're going to look at is density. The symbol for density, as we had gone through before, is the Greek letter rho. It's measured in mass per volume. So in our case, this is long tons per cubic foot, but it can also be in kilograms per meters cubed. Next, similarly, specific volume is denoted by a lowercase v, and instead of where density was mass per volume, specific volume is just the reciprocal or the flip of density, so it is volume per mass. Displacement, whose symbol is a capital Greek letter delta, is measured in long tons. Now over here on the right, we have four terms which everyone should be relatively familiar with already. We have length, L, which is denoted in linear feet, width, W, which is linear feet, depth, or height if you like to call it, which is H in linear feet, and then we have volume, which has a symbol of this capital V. However, to differentiate it from the lowercase v for specific volume, I've put this horizontal bar in the middle, and this is measured in cubic feet. All right, now going through that list, you probably realized you're pretty familiar with some, if not all of those terms, especially if you've served on a ship before. So let's go into a couple relationships that make all these terms come together. The first relationship we have is rho, which is density, equals 1 over the specific volume, which is lowercase v. I've already alluded to this before when I was talking about density and specific volume. Rho equals the reciprocal of specific volume. So mass per volume equals 1 over volume per mass. The second relationship we have is capital V, which is volume of a compartment, equals length times width times depth. Now, of course, there are many ways to calculate the volume of many different shapes. However, we're going to be using this in the context of flooded compartments. And on board a ship, compartments are typically either rectangular or very close to rectangular. So it's actually surprising how universal this formula can be. We know that volume is cubic feet. We know that length, width, and depth, or height, whichever one you prefer, are all linear feet. The next relationship we have is displacement equals density times volume. Or, as we'll typically use in this course, displacement equals volume of a compartment, or the volume of flooding water, divided by the specific volume of that fluid. Throughout this course, we're going to be using all these relationships in the context of ships taking on damage, whether it be hitting rocks and then flooding compartments, or if they are fighting fires, you have to use firefighting water which comes out of the ocean, which means that you're adding weight slowly over time, typically high, which means that you could be affecting your initial stability. These volume and displacement calculations are going to help us determine if we're harming or helping the initial stability. So let's take these relationships and make them into something more physical. We're going to take a look at the properties of common maritime liquids. This column here is going to have the liquid that we're talking about, as well as the temperature that they're assumed at, since density and specific volume change with temperature. We're going to have the density, which is going to be in metric units, and then we'll convert it into specific volume in English units. So to start it off, we have freshwater. This is something you'll find in the Great Lakes or similar pieces of water. The density of fresh water at 4 degrees Celsius is 1,000 kilograms per meters cubed. Converted into English, we have 36 cubic feet per long ton, and that's the specific volume. Similarly, we have salt water at 25 degrees Celsius. The density of this is 1,025 kilograms per meters cubed, so salt water is a little bit more dense than fresh water. Converting it to English and putting it into specific volume terms, we have 35 cubic feet per long ton. This number 35 is going to show up several times over the next couple chapters in different equations, typically multiplied by displacement. When we multiply this by displacement, it means that the formula is trying to extract a volume of added salt water. And lastly, we have diesel fuel, or DFM, at 15 degrees Celsius, which is right about 59 degrees Fahrenheit, 60 degrees Fahrenheit. Yeah, 59 degrees Fahrenheit. So we have a density of 900 kilograms per meters cubed. So you see it's much less dense. It's about 10% less dense as fresh water. And then converted to specific volume, it's 43 cubic feet per long ton. Alright, so concluding this video, we're going to take a look at 3 different scenarios that happen very rarely on ships. However, they do have certain considerations when it comes to the density of fluids that are being added or removed from a boat. In each of these scenarios, we're going to look at 4 things. All these are going to be introduced in later chapters. However, I just want to show you that with every single addition or removal of water or fuel or any type of liquid load, you're going to have several different things you're going to have to consider, and all of these are critical to the ship's stability. PS is parallel sinkage, so that's if you have a ship, if it sinks completely parallel, or there's also parallel rise, where it comes straight up out of the water. Trim, if this is the bow and this is the stern, trim is how they are related to each other. So is the bow going to sink a little bit more in the stern, or is the stern going to sink a little bit more in the bow? List, similar to trim, is the relationship of port to starboard. So where trim is the longitudinal view, so the long side of the boat, this is the transverse perspective of a ship. So list is something that is a permanent angle over to one side. If we have weight on one side, that's going to cause a list. And GM, or also called the metacentric height, is something that is an immediate number that pertains to the initial stability of the ship. Let's take a look at this first scenario, striking an object. Typically, when a vessel strikes an object, this object is submerged, so it's below the waterline. So you're going to have a large tear underneath the waterline, so seawater is going to be flooding in. How much seawater is going to be coming in? We're going to learn about the free surface effect and the free communication effect in this scenario later on in Chapter 5. However, just start thinking about the amount of weight that we're adding due to all this salt water. We know that salt water, it only takes 35 cubic feet for 1 ton of water. Now, if you have a large compartment that's open to the sea, you're adding a lot of weight. How is that going to affect your initial stability? How's it going to affect your GM? How's it going to affect parallel sinkage? Trim and list are also considerations. Firefighting. I alluded to it earlier. When you fight fires, you have to fight them with water. The only place you can get water on a ship is the ocean around you. So you're taking all this water here and you're adding it, if you have a superstructure fire like in this scenario, you're adding it very high up. A ship typically is designed to have a center of gravity right around the waterline, or its design waterline. If you're adding weight this high, you could be shifting your center of gravity a lot, which means that you're becoming more and more top heavy. And as you've seen in everyday life, things that are top heavy are very easy to knock over. Ships are no different. Lastly, we have what's called dirty ballast with a refuel. A dirty ballast system is something that a lot of ships might have. It is where you have fuel tanks, and when they're all spent, if you need ballast in an emergency situation, then you fill those ballast tanks with water, the seawater from the outside. Diesel fuel, as we saw, has a different density and a different specific volume than seawater. So your ship is going to change drafts, change trim, change parallel sinkage, change your GM, maybe drastically, maybe not drastically. Then when you pull into port, you have to have a contractor pump out all that salt water because it's contaminated with a little bit of diesel fuel. Then you have to fill those back up with diesel fuel. So now, after having one change out in the open ocean, you're going to have another change in liquid load and all the density and all the weight that's in the ship when you're at the pier. There's many different considerations when you're at the pier versus out in the ocean. How is that going to change the seaworthiness of your ship? All right, and with that, we've now come to the end of this lesson on fluid densities, the calculation of volume, and how they pertain to different shipboard scenarios. In the next lesson, I'm going to be going over ship nomenclature and the different parts of a hull. This is extremely important if you're talking with other engineers so that everyone's on the same page and knowing exactly what you're talking about. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.